Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to find the volume of a solid generated by revolving the given region about the line x-axis. Okay, so what does the region look like? We have the y equals radical x. We have y equals -1/2 x plus 4, which is a line. And x equals 0, that's the other name of y-axis, and x equals 8 vertical line. Let me just quickly show you how the region looks like. As you see that the region consists of two subregions, so two green regions. And on the left, you have the top part of that bounded by the purple line, and the bottom part is bounded by the blue curve, and as well the y-axis. And the second green region is bounded about by the blue curve. That's a parabola, and bounded below by the purple line. And also the x equals 8 vertical line on the right. Okay? And we're going to revolve this two split regions about the x-axis. So essentially for each subregion, sub-green region, we're going to get a different three-dimensional object. So let's see what they look like. Okay, so you roll this around, and this is exactly what we got. Okay, so essentially, if you look at the very left hand three-dimensional picture, so you have like a cone looking like three-dimensional object outside, and inner side you have a bullet look like inside. So we take that bullet type volume out of the volume of the cone, and then the second part here, as you see, you still have a cone. Which is the outer volume, and inside inner volume there's another little cone over there. We take that volume out. Okay, so in other words, think about the whole three-dimensional object, and on the left we take the bullet looking inner volume out, and on the right we have a cone looking inner volume out, so we get the three-dimensional picture of that. Okay, so let me just remind you quickly what the disk method is, and we can start hitting the road. All right, so this is a table that represents the volume of a solid of revolution by the disk method, and depending on what axis you're revolving around, you have two different formulas. In our case, x-axis is the axis of revolution, so it's a horizontal axis. So we're using the first column and the first picture over there on the left. Okay, so we essentially take a vertical slice, which is per to the axis of revolution from the region, okay, and that comes with thickness dx, and then you revolve that around the x-axis in our case, so you get a disk, and since the thickness is dx, so you're going to write the radius of the disk in terms of x. Let's say like you have r of x, and you can go back and write down the volume in the integral as like pi times integral from a to b, radius squared times dx. Okay, so I think this is already a long intro. I'm going to stop right here. So why don't you go ahead and start the problem? All right, let's see how the region looks like, because we have four equations provided to us. So we have y equals radical x. This is like a parabola type graph. This is a line, y equals -1/2 x plus 4. This is y-axis, and this is the vertical line, and the axis of revolution is x-axis. Well, first we need to find the intersection points if there's any, because we don't know exactly what the region looks like here. So let's check if there is any intersection between y equals radical x and the line y equals -1/2 x plus 4. So we have to solve this equation. So let's take the square of both sides to get x equals 1/4 x squared plus minus 4x plus 16. So now I'm going to multiply everything by 4. Okay, 4x equals x squared minus 16x plus 64. All right, so let's subtract 4x from both sides to get x squared minus 20x plus 64 equals 0. Okay. So here I need the zeros of this quadratic. Let me just erase this part real quick and try to come up with, let's try to come up with the zeros here. X squared minus 20x plus 64 equals 0. Okay, so I'm going to do it with my way, but you can use the quadratic formula if you want to. So we're going to find two numbers. So x times x, and I'm going to find two numbers whose product is 64, but the sum is going to be negative 20. Okay, the product is going to be plus 64, and the sum is going to be negative 20. So what could be those numbers? Well, I'll go with 16 and 4, and maybe minus, because the sum has to be negative 20, and the product has to be like 64. So this tells me that the correct factorization for this is x minus 4, x minus 16. So that tells me that one root is 4, the other root is 16. Okay. All right, so let's check how the region looks like now. So here we go. We got x equals 4 and x equals 6 for the intersection. Apparently, this graph here, the blue curve, which is the graph of radical x, is going to make a turn and then hit the line again. But in the problem statement, we are given that the region should be in between y equals radical x, the line, right, and y-axis, and the vertical line x equals 8. Here we go. This is our x equals 8 vertical line, and this is our y-axis, which is x equals 0. Okay, and 4 is the only intersection point. Since we want to keep the region in between the vertical lines x equals 0 and x equals 8. So so we have in fact two regions. First region is this one, and the second region is this one. Again, we are not interested in the other intersection point because that is not in our region. Okay. All right, so what we're going to do is to revolve this region around the x-axis. Okay, that's x-axis. Great. So one thing that we have to pay attention is that we have two different regions, and here, if you take a slice in the first region, okay, let's take a slice like this, and then let's take a slice as well in the second region. Let me just make this a little bit more looking like a slice. Okay. All right. So you got two different slices with, let's say, thickness dx and thickness dx. And here, what we're going to do is that, or maybe you should first observe this, that two regions are completely different, and the corresponding volumes as well are going to be different, because in this one, if you revolve this around the x-axis, okay, so you're going to get this kind of like washer, and if you roll this one around the x-axis, we're going to get this type of washer with both coming with thickness dx. But the major difference here is that the top part of this slice here touches the purple line, and the bottom part of that touches the blue curve. Okay, and in the other region, the second region, is the other way around. The top touches the blue curve, and the bottom touches the purple curve, starting from the intersection. Okay, so that determines the inner and outer radii in each case separately. So what I'm going to do is I'm going to split this green region into two parts, one on the left, one on the right, and then I'm going to use different formulas to find the volumes of the three-dimensional objects. But before I do that, I want to show you what the actual three-dimensional shape is, just for you to visualize it. So let me just show that to you. There we go. We have two functions crossing, as you see, and now we're going to revolve that around the x-axis. Okay, so we keep revolving, okay, revolving, and revolving. As you see that, you have On the left, you have one type of volume. On the right, you have another type of volume. So like here, so if this is the intersection, okay, and this volume is the volume of the horn, but you took out the value of the cone here, okay? And in this one, you have another horn type three-dimensional object, but you take out the volume of this piece here, okay? So that three-dimensional part taken out, okay? So, as you see, the volumes, the volume on the left and the volume on the right are like they're completely different, okay? So here we go. What I'm going to do now is to determine the inner and outer radii for the slice I picked here. And I'm going to do the same thing here, okay? Let me just rewrite everything for you. So let's get a thinner slice, okay, here as well, okay? One thing I'm going to do is the following. So I'm going to label this as, I'm going to label the location of the first slice as X. And same as for this one, I'm going to label that as X, okay? So let's say like slices are X units far from the Y-axis. All right, I need this distance from here to here, right? So from the bottom portion of the first slice down all the way to the axis of rotation. I'm going to call it like little r, okay? And I also need the distance from the top slice, top of the slice, to the x-axis, okay? Well, first off, the little r is depending on the blue curve because the bottom portion here touches the blue curve, okay? So that blue curve comes with the equation radical x, so this is going to be radical x, okay? And the top portion of the slice is determined by the line, and line comes with the equation 1/2 x plus 4. Okay? And in turn, when I have a disk, the volume, let me call it like 1, volume 1, pi times outer radius squared minus inner radius squared times dx. I'm not integrating yet, okay? And this comes with thickness dx. Obviously, this comes with thickness dx. Okay, this is the volume of the first one. Okay, so I'll just put the x here to save space. Okay, so now what I'm going to do here is to determine the distance from the bottom portion of this disk to the y-axis, and as well the top portion of the slice all the way to the x-axis. Okay. Now let's see what it is. Well, the bottom portion touches the line, so that is the equation. So that means the equation of the line, r equals negative 1/2 x plus 4. The top portion is touching the blue curve, so that is determined by the blue curve, and capital R for that reason is going to be just radical x. Okay, so for volume 2, I'm going to use the formula pi r squared minus little r squared. Okay, all right. Woohoo! So let me just write here 2 volumes, pi and pi. Okay. So the first one is for the first one, the lower limit is going to be 0, upper limit is going to be 4 here, as you see. Right, all x's are ranging in between 0 and 4. For the second region, it's going to be between 4 and 8. Okay, so I'm going to go back and put 0, 4, 4, 8. Okay, let's double check the capital R and R, little r in the first case. In the first case, capital R is the line, and the little r is the curve. Okay, so negative 1/2 x plus 4 quantity squared minus radical x squared dx. And this one is radical x squared the other way around, right? Capital R is radical x minus plus 4 squared dx. Okay. So after this point, we're just going to evaluate each integral, okay? So let's just do that. So v1 plus v2, in fact, we can add also at the same time. Pi from 0 to 4 plus 4x squared plus minus 4x, right? Plus 16 minus x. I'll just get rid of this plus sign here. Dx plus integral from 4 to 8 pi. I have the other way around, right? X minus 1/4 x squared minus 4x plus 16, right? Dx. All right, at this moment, I'm gonna let you do the calculations, okay? And I'm just gonna write down the result of these two definite integrals. The first one is 88 pi over 3, and the other one is 56 pi over 3. That adds up to 48 pi exact, okay? Again, this part is just integration by using the power rule for integration. Okay, and the use of fundamental zero calculus. That's gonna be tedious for my end, and then that's gonna make the video too long. Please do those calculations by yourself. Okay, and this tells me that this shape has the volume 48 pi. Okay. So yeah, to sum up, we in this problem we had two different regions to be able to write down the volume integral. And in each region, we sort of like try to utilize the washer method. We don't have any disks, but punctured disks or washers once you have the volume of revolution. Okay, so we sort of like handled each region separately. All right, I think that takes care of everything in this question. So I'm gonna just finish right here. And thanks for watching. And if you have any questions or comments, please send those to my way. I'll see you in another video. Bye.